and some specific aspects of this, results, conclusion, and future work. So, just to stress out some very important aspects when we talk about ambulatory platforms, there are some hot research topics that people are actually putting some effort in this time, which is the difference between application-specific integrated circuits or custom off-the-shelf. This is like the difference of building the whole system by yourself, or meaning by yourself is based on micro technologies and manufacturing, or actually building your system based on discrete components that you can buy, you can order from the available shops in the market. So the one that we are going to present today is the second type. It's the custom off-the-shelf components type. So number of channels, sampling frequency, signal resolution, data transmission, and power consumption are also very important aspects when we talk about EEG acquisition platforms. Another very important aspect is the platform itself, the kind of structure where you are going to build your system. There is a large difference between real-time and non-real-time operating systems in the way that you can actually accomplish your tasks in the specific time that you define, or if you don't have a real-time system, it might be hard to accomplish those specific times. Microcontroller to perform the real-time acquisition demands, that's the issue here, and the DSP, which is the digital signal processing, which is usually very important when you are dealing with signals, because you want to process your signals while you are also acquiring them and transmitting them to other devices. So these are very critical aspects when you're building a system like this. The work that we are proposing here is actually tackling these aspects in this way. So we are going to build a wireless and wearable platform. This is a platform that has a very large number of channels, high signal resolution, high sampling frequencies. It has a very differentiating characteristic, which is it is able to detect specific features of the signal that might be of interest for your application. In this case, we will talk today about epilepsy detection on this platform. And also the consumption, the power consumption is very important. So we are also addressing this and trying to make this platform as low power as possible. So the objective that we are pursuing with this platform is, so it is built on a single board computer system. It tries to use as much as possible low power components off the shelf, dry electrodes. This is also a very important aspect for us, since, as probably you have heard on previous talks, I actually talked about that yesterday on the brain computer interface tutorial, when I was mentioning that the time that you spend placing your electrodes on the subject is actually critical for the performance of the experiments. So we are tackling that using dry electrodes, which are faster to place. Signal resolution, high signal resolution, 24 bits, sampling rates, higher ones, also 1,000 samples per second, wireless transmission, and the algorithm that is going to detect the epilepsy events. So, regarding the system architecture, what you have here is mainly the sensing part of the system, which are the dry electrodes. Then you have the converter, which is the analog-to-digital converter, converts analog signals into digital signals. And then you have the platform itself, the single board computer system, where we had to develop a driver, a software part that is actually dealing with the converter, and the central processing and transmission unit, which is really the core of the system and is supposed to deal with data and transmission at the same time. So the first I would say, scenario for this platform is the one that you place this EEG platform on the subject's head, and you can transmit data wirelessly to just a device where you can visualize your data. This is the simpler, the simplistic approach. We are actually pursuing a different approach where you can actually deal with your data in a more complex way and still giving more functionality. So you have the same system and you can have a device in the middle, which is maybe a smartphone. This smartphone is able to actually visualize your signals and also to route your data to other systems, like, for example, a central repository. The idea of this approach is that either this can be a personal device where the subject, the user, can actually monitor his EEG. He can receive some interpretations, some measures about his EEG, but at the same time he's sending data to the physician, to the medical doctor that can actually acquire some diagnosis, or that can give some extra information to the patient based on the EEG. So this has been developed in a large project that is being developed in Portugal, in the University of Pinho. This is called the My Health project, and there's several models that actually can send data, wireless data, or generally medical data, to a central repository where you can integrate all data from EEG, ECG, from air analysis, from medical imaging analysis, and all of that imaging, all of that data are actually integrated in the whole system and can be visualized in a very integrative way, and lots of different aspects can actually be analyzed. So, going back to our EEG system, so this was the first prototype. This was a bulky one, as you can see. It was stabilized in acrylic cape. It had first very large dimensions, a little bit heavy. Then we are actually building the new one. It's already complete. So it is a 65 to 68.5 millimeters system. It is much more miniaturized than the first one. It is already being embedded in a cap like this one. So the idea is we are also working with a textile company in Portugal, a huge one, that can actually has the ability to embed these electronics in textile systems, where you can actually build a system that is not as social exclusion. It's not like doesn't cause a big impact on the way that you see people that are using this system. So it can also accommodate the batteries. It involves the inside cap where you place your electrodes, and an outside cap that actually gives this system some functionality, at the same time some design, probably stylish. Going back to the technical aspects. So this is based on a single-core ARM Cortex system. This is a wireless communication based on the Wi-Fi infrastructure, and it runs on a multitask Linux operating system, the OP solution. So this central processing and transmission unit is responsible for these main four functions. So it interfaces with the converter. It saves data in real time in the SD card, and transmits data wirelessly, and also process data. So this is these four main features you don't find on any system that has been at least published in the last times. The analog to digital conversion, it's ADS 1299, so it's from Texas. The main features of these converters are the number of channels, 8 channels, 24 bits resolution. It's 256 samples per second for 16,000 samples per second. It is very low power and it has a very low noise. The active dry electrodes that we are building, it is based on a 6x6 array of folded pins. It is the mechanical interface for the system, meaning that this is the place where you actually acquire the signals. It's the first stage of the system. It has a unity gain buffer embedded in the electrodes. So the idea is to cancel some noise right on the electrode, so the signal that you are acquiring can actually be transmitted to your amplifier with much less noise. So this is the textile that is being developed by this textile company. Then you have to, on one side you place the electrode, on the other side you place the cable, and this is the cable is where you can find the buffer. This might be a bit technical, but anyway I'll try to give general overview of this. So regarding the functionality of this driver, the idea is that you have the converter, which is the first place where you actually acquire your EEG data, and this driver is supposed to send data to this driver that is working on the embedded system. So you have bidirectional communication here, since you are receiving data, but first you have to configure your ADS so it works properly. Then in the driver, this is a memory map system, so every time you acquire a specific number of samples, they get in this second buffer, a flag is turned on, which means that the data is passed to the user space of the kernel. So then you have you access the raw data, save the data, band pass filter it, or any other signal processing functionality. Then you send data wirelessly to other devices. So this is the user space, that's the kernel space. Once this thing is finished, the flag goes back off, and the cycle of the data packet is complete. Okay. Regarding performance of this test, it is working very well actually. So it is. You can see here the time that we spent to accomplish this task. So for the actual acquisition of the samples, it's 427 microseconds for 768 bits, which is one sample of data, for the 32 channels times 24 bits. Then you acquire 1 second of data. That's the size of this buffer, 1 second of data, which takes 122 microseconds to copy the data to the second buffer. Then these are the times for each part of the processing. So you can see that those are very small times. In the end, the total time for the application is 140 milliseconds out of 1 second, which means that we spend less than 20% of the time with the acquisition, processing, and transmission. Why this is good? Because all the time that goes from 140 milliseconds to 1000 milliseconds, it's free time that we have in our processing system, so we can do more complex processing. We can do whatever we want because the main functionalities are already done in this time. Regarding power consumption, we have 500 milliamps per hour with wireless on and 250 milliamps with wireless off. Regarding key event detection, the epileptic event detection, it's working in a way that we can actually, while we are acquiring, we can detect if each data packet is actually respected to epileptic events, or if it is normal data, or in other way, if it is artifact data. Artifacts can be due, for instance, to eye movements, to muscle movements, but we can actually differentiate the three different kinds of data. So we are actually, with this system, which is based, I'm not going into details of the signal processing part, this is not really the topic of this presentation, but it is based on an algorithm that actually uses the effect, the root mean square value of the signal to actually differentiate between normal data and epileptic data. The resolution, or actually the accuracy that we are actually getting these times, it's about 95% of detection rate, and the false positives, it's around 1%. So the main development and the main innovation of this platform here that I'm presenting, it's really the way that the operating system is dealing with data. Usually on a Linux kernel driver, you have the scattering attributes and priorities, which are defined by default, and by that we got for 427 to 1221 microseconds to accomplish all the tasks of this platform, which is higher than what we need. So it's very unstable, and it's hard to tune these times. Once we were able to get the real-time constraints in the same operative system by using the SCAD FIFO algorithm and using very nice values, which means that it took some time to adjust these values, we actually could get all the tasks done in this very tiny range, which is really the secret for this system to work. So multitasking with real-time constraints it actually helps this thing. By comparing this system with others, you can see that there are many things that we could see here. I'm just highlighting some, which is the number of channels. You can see on the top row. The one on the left is the one that we are proposing is much better than the other ones. Then the signal resolution is pretty high here in the third line. And also you can see from the consumption. So it's 0.2 nanoamps per hour per bit, which is very good for a system like this, especially with the kind of functionalities that we have now. So we also developed the visualization system for this data, and it was based on C# language, and we were actually able to validate the system by using the very common paradigm for EEG detection, which is eyes closed, eyes open. You can see the respective signal, and during the eyes closed phase, you can see the alpha rhythm, which is really the watermark for EEG. Okay, so this is an artifact. So this is also very easy to detect. And just to conclude, so we were able to develop an overall system with minimum delay. It has a reasonable time frame to do all the functionalities, acquiring data and processing it. Low power consumption. It actually is able to detect epilepsy detection, detect epilepsy events, and it's still working ongoing project to make it even better. Okay, thank you.